Okay, this is worksheet number 9 on self-inductance and geometric optics. So we have our self-inductance equation, and it's kind of the important thing in how it relates to EMF is that an EMF can be induced in a current carrying coil by changing the current, magnetic field, magnetic flux itself that is intrinsic. So in all previous cases, our magnetic field came from an external source, we had like a magnet there, or we just draw in the field that exists there. But with self-inductance, the change actually occurs within itself. So that's why we can consider an RLC type question a magnetism question, because it has a relationship to that EMF. And we have our RL circuit equation, that's number 2. And then that will move us on to geometric optics, starting with the law of reflection. So basically this equation, the angle of incidence, so that's going to be the angle between the incoming ray of light and the surface, is equal to the angle of reflection, and that's going to be the angle that is reflected off the ray within the surface. And then we can look at Snell's law. We basically have the index of refraction of one substance as the ray goes into the other is going to be equal to the index of refraction times the angle at which it exits. And I'm going to draw something out and that basically summarizes this equation entirely. And I'm going to bring up all the key points related. So, oh, thanks. Let me get the share going. Okay, so let's imagine we have this surface, and we'll say that there's water in here, right? And down here, we'll have our index of refraction 1 and 2. We have some ray that comes in and goes through the surface. And then the question kind of is visually, how does the ray exist? Is it going to be something that looks more, sorry, let me try to make this a little bit more zoomed in to be clear. Is it going to be something that leans more towards this normal, or it's going to be something that leans away from the normal? Well, that has to do with the index of refraction values. So when you go from low to high index of refraction, so that means when you go from N1, which is lower, than N2, which is higher, you bend towards the normal. So it looked like something like this. And what's the normal? It's just the name of a line that's perpendicular to the surface that you're penetrating. And that's an important thing. The normal is the line that is perpendicular to the surface that you're penetrating. And of course, the alternative is if you go from high to low index of refraction, you bend away from the normal. So that will look something more like this. So in our cases, let's say we're going from low to high and we're bending towards the normal. The question then is, which is the angle of interest? With Snell's law, remember we have N1 sine theta 1 is equal to N2 sine theta 2. Well, the angle of interest is always touching the normal. So this is theta 1, and this is theta 2. I'm going to say not right now, very in big letters. So remember this. The angle right here is not that angle of interest. We can use it to find the angle of interest, but what you plug into Snell's law, or what the output of Snell's law is the angle between that ray and what's touching the normal, where again, the normal is perpendicular to the surface that we're impacting here. And then the index of refraction, we have n is equal to the speed of light in a vacuum. So that's 3 times 10 to the 8th meters per second. And that's going to be divided by the speed of light in that certain medium. So you can calculate n if it's unknown. All right, let's proceed to our RLC circuit question. So this is question number 1. And it's kind of long-winded, but it's just to really hit all the key points related to this. Even though it's, a lot of numbers and stuff, I think the qualitative points are more powerful. So we have this RL circuit. Sorry, there's no capacitors, but kind of the same principles apply. We have this RL circuit, and it's connected to a 24-volt battery. The switch is closed at time equals 0 seconds. Now, I'm going to say something that's just going to be very important to solving these questions when we're dealing with inductors. So at steady state, the current is constant, and inductors act as wires. That means, it's just flowing across freely. However, inductors act like an open switch immediately after closure. So therefore, if we consider, let me put the screenshot of the diagram into my document here. Okay, so at time equals 0, that means immediately after closure, inductors act like an open switch. So when we have an open switch, I'm going to draw this in red and just be very very bold about it. So you get my point. When we have an open switch, we're not going to have any current moving on through this way. So in part A, we're asked to fill out the table in the instant following closure. The instant following closure. The switch is open. Well, the first thing we want to find is I1, and we know I1 exists right here. And then also I2, which is over here. Well, I1 can be calculated by a simple Kirchhoff's. Let's call that loop 1. And when you work out loop 1, I'm not going to go through how we do this. We should be comfortable with this at this point. We'll see that when we start 0 is equal to 24 starting behind the battery minus 8 I1. So that means I1 is equal to 3 amps. And I don't have the table here, but whenever I write something that should go in the table, I'm going to put a green check mark next to it so that we know what I1 is. And then now, per the reasons we've already discussed, this is an open switch. That means there's no current that's flowing through here, and rather I2 is going to be equal to 0 amps. Done. And then what's the change in I1? Well, there is no change in I1 over time. There's nothing over here that's an inductor or that's going to be changing with the amount of time. You know, the amount of current I1 here is going to be the same thing at time 0 versus time, you know, down the road when we reach steady state. So that means the change in the current of 1 divided by change in time is going to be equal to 0 amps per second. There's going to be no change. Now, the difference is with I2 over delta T, there is going to be some change because recall, right after closure, it acts like an open switch. However, at steady state, it becomes a constant current that's flowing all the way through here. And the way you want to think about it is, in the case of an inductor, when a switch is closed, the inductor is initially a short circuit, and this allows a large amount of current to flow through it. However, a magnetic field will slowly build up and eventually reach the steady state value. And the rate of change of the current with respect to time will be higher immediately after the switch is closed compared to when the circuit has reached steady state. So it's going to be higher immediately after closure rather than when it reaches steady state. That means for part 4 in part A, this value is going to be bigger than part 4 and part B. That's kind of this qualitative thing. Now, how do you actually calculate that? Well, again, we can use Kirchhoff's rule. We can do a big loop, call this I2, and it's going around everything. So with I2, we're going to start, bad circle. We're going to start with a 0. It's going to be equal to 24 minus 12 I2. We already talked about what I2 is equal to 0 right after this closure, minus L over the change in I divided by delta T. And this is for the second guy right here. Okay, and this is the equation that I actually gave you on the first page called equation number 1. When you work this all out, you'll end up solving for that value as delta I2 over delta T is going to be equal to 4 amps per second. Okay. Now, within part B, we're asked to calculate at steady state. So per the reasons we've already discussed, I1's not changing. There's no inductor there. There's nothing that's going to be changing over time. We've already showed that the change in current over time is equal to 0. So therefore, I1, again, is going to be equal to 3 amps. Okay. Now, I2, this is different now, because when it reaches steady state, the inductors act as wires. So when you consider doing your loop equation again, we'll use the same I2 as before. We'll rewrite everything. There's no longer a change in current over time as it's acting like a wire. A wire just is a wire. It just allows the same amount of current go through as always. So now you just need to resolve for this I2. And when you solve for I2, it will come out to be 2 amps. Okay. This finally takes us to parts 3 and D of part B. I'm going to say it again, per the reasons we discussed, there is no change with respect to I1. However, with I2, it's going to be smaller than what we found previously, and we talked about why. And also, let me just write that real quick. And how we actually solve that is something we've already discussed. It's a wire. At steady state, an inductor acts like a wire. That means the current going through it you treat it like a wire. It's going straight through like that. So therefore, there's going to be no change at steady state. So I2 over delta T is equal to 0 amps per second. So this question is very important, like the important parts, kind of what I said over and over again. And you can see how the same concept was hit over and over again. The thing to take away is, inductors act like an open switch immediately following closure. And then, I'm sorry, at like the time immediately after, what do they say? The switch is closed at time 0. So yeah, an inductor acts like an open switch immediately after a closure. There's going to be no current over there. And then at steady state, it behaves like a wire. So therefore, you can calculate I2 through the way we discuss, and the change in I2 over time will be equal to 0. Okay, let me see if there's any questions on this. Okay, question number 2 here. We have an RLC circuit. We know the resistance, we know the capacitance, we know what the inductance is, we know the RMS value, is that the VRMS, and then we know the frequency, it's 600. Okay, so what we're asked to determine is the RMS voltage across each of the 3 circuit elements, right? Now to calculate this, the first thing you'll need to do is find impedance value. And how do you find that impedance value, which itself is basically the resistance of everything in that system, right? We have an inductor, a resistor, a capacitor. What is the resistance contributed by each of them? That's what the impedance tells us. That's that Z is equal to R squared plus XC plus XL squared, like this. Well, we know what resistance is, but we don't know XL or XC. So we need to first find those. Where XL is equal to 2 pi F times L, which in this case is equal to 22.6 ohms. And then XC is equal to 1 over 2 pi frequency times the capacitance, which is equal to 10.6 ohms. We now just have to plug in the resistance, and you can see everything's in terms of ohms. So when you end up solving for that total impedance, it's in terms of resistance. So it's 27.7, and that's the resistance through the whole system. Now, to find the VRMS across each of the circuit elements, what you need is the current at the RMS current. And to solve this, we can use a modification on Ohm's law, which is VRMS is equal to IRMS times the impedance value we just solved for. Do a little bit of rearranging, and you can see, sorry, let's do this. Do a little bit of rearranging, and you can solve for that IRMS. And IRMS is going to be equal to 0.36 amps. And now kind of the fun part is you got to plug in everything into solving the RMS values across each of these circuit elements. So this is what we're going to call part 3. Here, across the resistor, we have IRMS times R. For the inductor, we have IRMS XC. Oh, sorry, my L's and my C's sometimes they're close to each other. And now all you have to do is plug in and solve. So here we have 9 volts, here we have 8.14 volts, and here we have 3.82 volts. Okay, so what's my process here? You find the impedance, you determine the RMS value of the current through the circuit, and then you find the RMS voltage across each of the circuit elements. We're next asked to determine whether the current leads or lags the voltage. Well, to do that, you're going to need to calculate phase angle. And depending on its sign, that being greater than or less than 0, you're going to be able to determine if it leads or lags. So this is part A. For part B, use the tan phase angle is equal to XL minus XC divided by R. Solve for that value, and what we end up with is 25.6 degrees. And then because this angle is greater than 0, that tells us that the current lags the voltage. Okay, so the whole thing with phase angle doesn't really come up that much, but I just wanted to make sure I hit it for continuing. And we've also done a problem like this on a different worksheet. Hannah, go ahead.
Could you go over why it lags the voltage one more time, please?
Oh yeah, let me pause this. So, okay, so moving on to question 3, we have light is incident on an equilateral glass. That means every side of it's 60. Prism at a 45-degree angle on one side, and then we want to calculate the angle at which the light emerges on the opposite. So, I mean, this couldn't get more like classic for these type of Snell laws questions. We have this prism right here. We know that the index of refraction of glass is 1.54. And now here we have air, let's call it Na, is equal to 1. And we have this ray of light entering the surface. And remember, our normal is always going to be perpendicular to the surface. So it's actually pretty nice to draw the normal first. We have our ray coming in like this. And we know it's 45 degrees, and it's always the angle that's touching the normal, 45 degrees. And then through this, it kind of, bounces around in here. And it comes out to some angle, theta 2. We don't know what that is. And then it comes out the other end. And there's going to be some angle right here. And let's just call what we're looking for altogether alpha. Okay, so the first thing we need to do is calculate what theta 2 is equal to. And theta 2 can be calculated nicely by using Snell's law. So and you were going to work all this out, you're going to rearrange, and you're going to get theta 2 is equal to 27.8 degrees. So the next thing we're going to do is need to find this angle over here. And that angle will tell us how to solve for alpha through Snell's law. But to do that, we're going to need to do a few intermediate steps. So the first one I'm going to do, we know it's an equilateral triangle, so 60 degrees up here. The first thing I'm going to do is calculate theta 3, then find theta 4, and then through that, I can find theta 5. There's many ways to do this, but I'm going to kind of do the long way just to kind of, show how to do it. So with the relationship between theta 1 and theta 2 and theta 3 is that there's 90 degrees. So that means to calculate theta 3 from theta 2 is going to be 90 minus theta 2, which we just solved for, is equal to theta 3, where theta 3 is going to be equal to 62.2. Now, using that relationship, we can find what theta 4 is equal to because we have a triangle at the top there. So therefore, we can say that 60 degrees plus theta 3, which is 62.2, plus theta 4 is equal to 180. And here you have enough to solve for theta 4. And now theta 4 is equal to 57.8. And now we can solve for theta 5, where that's going to be this angle right down here. And again, that's because this is perpendicular, so it's equal to 90 degrees. So to solve for theta 5, it's going to be 90 minus theta 4 is equal to theta 5. Theta 5 is equal to 32.2 degrees. You can now apply Snell's law like we did in part 1, and you'll find that you're now escaping the glass. So n of the glass, theta 5 is equal to n in air, sine theta 6, which is our angle of, I should call it alpha, like I did before. Alpha, which is our angle of interest. Work that all out, and you'll get alpha is equal to 56.3 degrees. So question 4 now, we have the bottom of this pool. There's a detective shining his light on it, and he's 1.3 meters above the water into the surface. We give him the index of refraction. And actually, the one for water, I think you might need to memorize, 1.33. At a point that's 2.5 meters from his foot at the edge of the pool. And we want to know, where does the spot of light hit the bottom of the pool, of the 2.1 meter deep pool, measure from the bottom of the wall beneath his foot? So I'm talking about a lot of things. I think the important thing here is to draw it first, because that will really clear things up. So if we can imagine our pool ledge, this nice and deep pool, and we have our water, and we have our detective right here. And we're told the detective is holding their light at a distance that's 1.3 meters above the ground. We're going to call that height 1. We're also told that the pool is 2.1 meters deep. We'll call that height 2. We know that the light that emitted enters the water some 2.5 meters away. So we'll call that length 1. So from here to where it enters the water, we'll call that length 1. Okay, and we have to draw the normal, which is going to be perpendicular to the surface entering this. And then out of this, there is an angle of reflection that looks like this. Okay, and we want to find that total length from where the detective is standing to where that light comes in. That's what we'll call L2. What is L2 made up of? Well, it's made up of L1, and then also this distance D. That's going to be the distance from here to here, right? You see that. Now to solve that, it's going to be a simple Snell's law application. So we have here the water, so I'm going to write NH2O equals 1.33. And then here it's in air, so it's equal to 1. And we're going to have this what's it called? This ray going into the water. So the first thing we need to find are our angles. So let's call this theta 1. That's going to be the angle from the detective's light and the beam it emits. And if you have a good eye, you'll know that that theta 1 is going to be equal to this theta 1. And that's actually our angle of interest that we're going to need to plug into Snell's law. So what is theta 1? We can calculate that by using a tan function. We'll say tan theta 1 is equal to L1 over H1, and theta 1 is equal to 62.5 degrees. Okay, and now in part 2, we can use Snell's law to find what theta 2 is equal to, where theta 2 is going to be this angle right in here, theta 2. So Snell's law, N through air, theta 1 is equal to N through water. That's going to be theta, oh geez. Theta 2. Solve for theta 2, that guy comes out to be 41.83 degrees. Now knowing theta 2, you can calculate D, which we need to add to L1 to solve for L2. So how do you solve for that? Well, let's call this part 3. We're going to have tan theta 2 is going to be equal to D over H2. Therefore, D is equal to H2 tan theta 2. And H2 is something we know. Theta 2 is something we found. We now have enough to solve for L2. L2 is equal to L1 plus D. And you know, L1 is something we know, and we already talked about what this guy is over here. So you can solve for L2, which is going to be equal to 4.38 meters. All right, any questions?